Hello everyone, good morning. Welcome to the live lecture of Doubtnut. So we were doing the chemical reaction of haloalkanes and we have already done part 1 of it, in which we have understood the type of organic chemistry reactions that can happen, right? We have understood what is nucleophilic substitution, we have understood what is nucleophilic addition, electrophilic substitution and electrophilic addition. These are the common reactions which are commonly found in organic chemistry. So we'll start with the chemical reactions of haloalkane. We'll understand how the haloalkane usually show your nucleophilic substitution reaction. So let's start. This is lecture number 10. If you don't know me, allow me to introduce myself to you. My name is Shagun and I've done my masters in chemistry from Miranda House Delhi University. I've added few qualifications. If you want to give a look to it, you can. Otherwise, we can skip this portion, right? Okay. So what are we gonna do? We'll understand the chemical reactions which haloalkane show. We will understand why a nucleophilic substitution reaction commonly shown by nucleophilic substitution reactions commonly occur in haloalkane. These nucleophilic substitution reactions can be further divided into two categories. One is SN1 reaction, other is SN2 reaction, that is nucleophilic substitution reaction with respect to or with first order is SN1 and with second order reaction is SN2. We'll give a complete detail, we'll do complete detailed explanation and study of SN1, SN2 reactions. But let's understand what is nucleophilic substitution reaction and why haloalkanes usually show nucleophilic substitution reaction. Whatever we did before, I'll give you a quick recap for that also. So let's start, but before that we have a small announcement. A small announcement is that Doubtnut is launching a new VIP course for class 12 students. This will be taken by our top teachers. They have given proven best results. There will also be doubt clearing sessions in it. They are your teachers. Their videos are available on Doubtnut app as well as YouTube channel. You can go and look their videos too. All you need to do is download Doubtnut app and there you will see the way how to use your app. You will have all the recorded lectures there. We'll give you homework after every class. There will be weekly test. There will also be books available for you with NCERT solutions. Timetable will be followed and proper teacher notes will be provided to you. You can see the live lectures as well as recorded lectures. That's up to you, whichever you are comfortable in, right? The best result from the previous year is Harsh Kumar was the district topper of Aurangabad, Bihar, who scored 91% in class 12. Shreya Ishani, district topper East Champaran from Bihar, again 91% class 12. And we have more than 100 students who have got 85% marks, right? Doubtnut, as you know, is the #1 institute in solving your doubts. We provide you homework, notes as well as tests, and all the video solutions are available in your classes, right? Okay, if you wish to see classes, you can see live classes also, as well as you can see the recorded lectures, whichever you are comfortable in. If you have any doubt, you can click the picture of that question and find the solution of that question on your Doubtnut app, or you can make a comment in your comment section during the live class and respective teacher will answer and verify your doubt, and you can get you also get notification to it and you can check your solution, right? Whenever you click the picture on Doubtnut, click the picture of the question and find the solution on Doubtnut app, you can get text solution. You also get video solution of that particular question too. If you have any doubt, you can call at 0124758250 or make a comment in the comment section. Now please let me know through the poll whether you are interested to join this class 12th VIP course or not. Whatever is your answer, you can write that in the comment section or you can use the poll. Okay, so let's start. We also have one small announcement. The announcement is that Doubtnut is organizing and has launched an English speaking course for you all guys. Our top teachers will be taking this course and it has already started from 8th July 2021. Whatever you have missed till now, you will get that in the recorded lecture form on Doubtnut app in the course itself. If you want more details, you can check out the comment section. We have given you a description link. You can check the description link to it. Okay, so let's start. We were on haloalkanes and haloarenes. We have completed the preparation methods of it. We've also completed the physical properties of haloalkanes as well as haloarenes. Now we were on the chemical reactions of haloalkanes. As I told you, in an organic chemistry, the general representation of a reaction is you need substrate. For organic chemistry, substrate is the one who is being attacked, and we need reagent. Reagent is the one who attacks the substrate. Both needs to be dissolved in solvent. If there is any pressure temperature condition required, you mention that on the arrow. You get product as well as you get byproducts with it, right? This is the general representation to write your organic chemistry reaction. As we have already discussed, the substrates can be categorized into two parts. I'm giving you a quick revision or a recap what we did in the last class, because it has been a while. Okay, substrate was divided into two parts. One was electron rich substrate, another one was your electron deficient substrate. Electron rich substrate includes pi bonds. Pi bonds have weakly held, pi bonds are weak bond, they have loosely held electrons. They have loose electrons and hence they act as your electron rich substrates. For example, your benzene was electron rich substrate, your pyridine, pyrrole, everything, pyrrole, your furan, they are your electron rich substrate. You have naphthalene, anthracene and so on. Anything that has pi bond acts as electron rich substrate, because pi bonds have loosely held electrons and they act as electron rich substrate. We also have electron deficient substrate. Electron deficient substrate usually includes the carbon carrying complete positive charge or carbon carrying partial positive charge in the form of delta positive. For example, a carbocation, if I talk about, is electron deficient substrate, right? We also have haloalkanes. Haloalkanes, for example, are generally represented as Rx. We have already discussed X being your fluorine, chlorine, bromine and iodine, your halogen groups. They are more electronegative than your carbon atoms, more electronegative than carbon atom, right? So, if we talk about the bond, the sigma bond that exists between R and the halogen group. R is normal alkyl group, that is the carbon and the halogen group. X being more electronegative takes the sigma electrons through the inductive effect and a partial negative charge develops on X, whereas the partial positive charge develops on your alkyl group. The partial positive charge on alkyl groups makes it electron deficient substrate. We have already discussed it. So these two were your electron deficient substrate. Then later we discussed that your reagent was also categorized into two parts. Reagent can also be categorized into two parts. One is electron rich reagent. Electron rich reagent is usually and commonly known as nucleophile. Nucleophile can be negative charge as well as they can be neutral form. So nucleophiles can also be further divided into two parts: negative charge carrying nucleophile, or we have neutral nucleophile. If I talk about negative nucleophile, we have OH minus, phenyl S minus. We also have R dash O minus, NH2 minus, RNH minus. They are your negatively charged nucleophiles. They have negative, and negative exist in the form negative means they are electron rich. If I say water, H2O is represented by this form. What happens when OH minus is formed? It is actually that the OH bond, the electrons in the OH, one of the OH bond is completely taken by the oxygen atom. This is hydrolytic cleavage, and oxygen develops in negative charge. The negative charge represents the two electrons from OH and H, O and H sigma bond. So this negative is just the increase in electron density, and hence we consider the negative as two electrons, and they generally represent electron rich things, right? So these are negative nucleophiles. We also have neutral nucleophiles. For example, we have water. The lone pair exists on oxygen atom of water. Similarly, we have ammonia, RNH2 and so on. They are neutral, but they have a lone pair, hence they act as electron rich reagent, right? Okay. Then we also categorized your reagent into electron deficient reagent. Electron deficient reagent were your electrophiles, were called your electrophiles, and electrophiles were also further categorized into two parts. One is positively charged carrying species. For example, your R positive, RC double bond O acylium ion, right? They are your electrophiles. They are electron deficient. RCO positive. If you see the Friedel-Crafts acylation reaction, if you know the Friedel-Crafts acylation reaction, we take RCOCl with AlCl3. AlCl3 is electron deficient. It takes up the Cl minus from your RCOCl. Hydrolytic cleavage takes place between carbon and Cl. That is, both the electrons of carbon and Cl bonds are taken by Cl, and hence positive charge is developed on carbon and a negative charge is developed on Cl minus, which satisfy the electron deficiency of AlCl3, right? AlCl4 minus is formed. With that, we have acylium ion. This acylium ion, since electron density has been shifted to your Cl atom, this becomes electron deficient, and hence electron deficient species are known as electrophile. This is positive electron deficient species. We also have neutral electrophiles. For example, we have BF3, we have AlCl3, and we have CO2. CO2 is actually the substrate that acts, that should come here, right? Okay, CO2 is the substrate. These are your electron deficient species, because if we talk about boron has 3 bonds with fluorine atom. Every bond, whether it is coordinate, whether it is sigma, whether it is ionic, it has 2 electrons only. So BF bond, we have 3 F bonds, and every bond has 2 electrons. Total electrons of boron are 6 electrons. It is less than 8 electrons, and it is unstable, or we can say they are electron deficient, or we can say they are Lewis acids. So these are your categorization of reagents we have already talked about. Later we said that substrate and reagent, for a reaction to happen, substrate and reagent first of all shows attraction. There is attraction between substrate and reagent. When they attract, they collide. During collision, some amount of energy is released. During the release of energy, some old bonds are broken and new bonds are formed. Old bond breaks and new bonds are formed, which further leads to the formation of your product, right? So the main thing for a reaction to occur is attraction between your substrate and reagent. There should be attraction between your substrate and reagent. For attraction, they should be opposite nature. They should be of opposite nature. For attraction between substrate and reagent, the substrate and reagent should be of opposite nature. They should be of opposite nature. That is, when substrate is electron rich, your reagent should be electron deficient. for attraction to occur. If substrate is electron rich, your reagent should be electron deficient, and electron deficient substrate and electron rich substrate and electron deficient substrate will attract towards each other and will show a particular type of a reaction. As we know, electron deficient reagents are called electrophiles, and we usually see electrophilic reactions in it. Whenever electrophilic or electrophile as a reagent is shown in the reaction, they will show electrophilic reaction. That is, when electrophile attacks the substrate, then it shows electrophilic reaction. When nucleophile attacks the substrate, it shows nucleophilic reaction, right? Okay. So, if substrate is electron deficient, then reagent should be of opposite in nature. That is, reagent should be, for attraction to occur, reagent should be electron rich. Electron rich reagent is known as nucleophiles, and whenever nucleophile participates in a chemical reaction, they usually show nucleophilic reactions. Right? Now let's talk about your haloalkanes. If I talk about haloalkanes, as you know, a haloalkane is R and X bond. X being electronegative develops negative charge, and R alkyl develops partial positive charge. This is electron deficient substrate. As already discussed. We require electron rich reagent for it. Electron rich reagent is known as nucleophile, and whenever nucleophile is used in a chemical reaction, they show nucleophilic reaction. In this case, in haloalkanes, nucleophilic reaction which is commonly seen is nucleophilic substitution reaction. In haloalkanes, nucleophilic substitution reaction is commonly seen in the chemical reaction with your haloalkanes, right? Now, what is the mechanism of nucleophilic substitution reaction? But before we go into the mechanism, let's understand what the word substitution actually means. Substitution actually means replacing. When nucleophile replaces one of the atom from the substrate, then it is substitution reaction. If I say nucleophilic substitution reaction, it generally means this is R delta positive, this is X, which due to electronegative develops delta negative charge. We have reagent that should be opposite nature of your substrate. That is, we have your electron rich reagent, that is nucleophile. Now, nucleophile and R have opposite charges. Nucleophile has negative charge, alkyl part has positive charge. They will show attraction. Nucleophile goes closer to your alkyl part in your haloalkanes, and then they have undergo certain collisions. Energy is released, and what actually happens is a new bond between nucleophile and R is formed, and the old bond between R and X is broken. After collision, new bond between your nucleophile and alkyl chain is formed, and old bond is broken. Old bond breaks, right? This leads to formation of your nucleophile and R bond. This is your final product, and X minus is leaves its position. The bond is broken and it takes the electron, and X minus is known as leaving group. It is known as leaving group. In haloalkanes, we have X minus as leaving group, and whenever we have a leaving group in your substrate, they usually show they usually show your substitution reaction. Since in haloalkanes X minus there is a leaving group, they will show nucleophilic substitution reaction, and it is generally represented in this manner. We have nucleophile that attracts to your alkyl part of haloalkane. Because it is positively charged, new bond between nucleophile and alkyl part is formed, and X leaves as a leaving group. This is the final product. And this is what a nucleophilic substitution reaction is generally represented in your organic chemistry. Is generally represented as in your organic chemistry. Okay, so this is been taken from your NCERT book. Now you'll completely understand. Nucleophile has negative charge, carbon has positive charge. There is attraction between positive and negative. Nucleophile attracts, new bonds between carbon and nucleophile is formed. X is removed in the form of X minus, right? So this is the way. Now nucleophilic substitution reaction can happen by two mechanisms. Nucleophilic substitution reaction can occur by two mechanisms. We'll discuss this later. They are your SN1 mechanism, that is nucleophilic substitution reaction with first order, nucleophilic substitution reaction with second order. We'll discuss this later. Let's see some examples of nucleophilic substitution reaction. So this is the big chart that is given in your NCERT question. This is the general representation of your nucleophilic substitution reaction. That is the substrate Rx, which is electron deficient, nucleus attacked by nucleophile, new bond between R and nucleophile is formed, X minus is released. This is substitution reaction because nucleophile has replaced X from your substrate, and hence this is replacing or substitution reaction, right? Okay. So here are your some of the nucleophiles. Remember what are nucleophiles? Nucleophiles are electron-rich species. They are either negatively charged or they are neutral with the lone pairs on one of the atom, right? If I talk about NaOH or KOH, Na always has positive charge. OH exists as OH minus. Similarly, K positive, OH minus. The nucleophilic part of NaOH and KOH is OH minus. What happens if RCl is reacted with NaOH? As you know, R develops positive charge because of less electronegative. OH minus acts as a nucleophile. OH minus attacks R, removes Cl, it forms a new bond, and Cl minus is being released. From your haloalkanes, a new group of a new functional group has been formed. Then this functional group is known as alcohol. So if you react your haloalkanes with OH minus ions, you can form haloalkanes. Now you can form your alcohols. Now preparation of alcohols from your haloalkanes are either by using your negatively charged nucleophile in the form of OH minus or using your neutral nucleophiles such as water. Water too acts as a nucleophile. As you know, water has lone pair. The oxygen atom in water has lone pair. This is electron rich. It will attack your R positive and remove Cl minus. Oxygen gives its lone pair, and whenever a lone pair is denoted, a positive charge is developed. Cl minus release takes this H positive and you again form ROH, and HCl is released as the byproduct. Now also this leads to the formation of alcohol. From haloalkanes, how do you prepare your alcohol? Using your negatively charged nucleophiles by using their salts such as NaOH or KOH, or using neutral nucleophiles such as water on your haloalkane reaction leads to the formation of alcohol. So this is also the way to prepare your alcohols from haloalkanes. Let's understand the next part. So this was the preparation of your alcohols from your haloalkanes. Let's understand how ethers are formed. Since Na and NaOR is taken, as you know, Na is taken as Na positive, R dash O minus acts as a nucleophile. Now the reaction is quite similar. You take haloalkane with NaOR dash. OR minus acts as a nucleophile, attacks carbon, removes Cl, and a new bond between your R and OR minus is formed. Cl minus is released. Na positive, which is present in the salt, takes the Cl minus and forms NaCl, right? So this is the new functional group ROR, which is known as ether. How to prepare your ethers from haloalkane is using your NaOR as your reagent, right? If I talk about NaI, I minus will be the nucleophile. I minus will replace the Cl. I minus will replace your Cl minus and form Ri. We have already discussed this in preparation of your iodoalkanes. This was your Finkelstein reaction, right? If I talk about ammonia, what happens is if RCl or any Rx is reacted with ammonia, nitrogen has extra lone pair. It attracts delta positive charge of the alkyl part, removes X minus R. Nitrogen has given lone pair, a positive charge develops on it, and X minus is released as your leaving group. If I open the bonds of hydrogens in the ammonium group, it has 3 nitrogens, a lone pair is given, hence positive charge is developed. X minus takes the H positive leaves the electron, positive and negative charge neutralizes each other, and RNH2 is the final molecule that is formed, and HX is released. So how to prepare your amines from your haloalkanes is by using your NH2. So amines are prepared, right? Similarly, you can react with R2NH2. New bond between R and RNH2 will be formed, and in this way you can prepare your primary, secondary and tertiary amines. We'll discuss this in quite detail once we individually do the preparation method, but here are some important nucleophiles, for example KCN and AgCN. Also we have KNO2 and AgNO2. They both cyanide ion, they both releases Cn minus ion, right? Now Cn minus acts as your ambident nucleophile. We'll discuss about ambident nucleophile later. Similarly ONO and NO2 minus, they are your ambident nucleophile. We'll discuss this later and we'll complete this chart tomorrow, because first of all let's understand how much have you understood till now. So let's do quiz first. We'll continue this. The quiz is very easy. Just keep in mind your basic things and you will be easily able to do the quiz. Before quiz, I would like to tell you something, that when is your substitution reaction easy and when is your substitution reaction difficult. If I say your Rx and nucleophile, if I say haloalkanes undergo nucleophilic substitution reaction easily than alkyl, then your aryl or your haloarenes. The reason behind that is, please write this statement: haloalkanes undergo nucleophilic substitution reaction reactions easily in comparison to your haloarenes. That is, if I say I have CH3Cl and I wish to convert into iodoalkane, iodomethane, what I'll do is take NaI as your reagent. NaI is a source of I minus. I minus will attack your carbon delta positive and remove Cl minus, and we finally get CH3I and Cl minus is removed. This reaction happens easily. This substitution reaction with haloalkane happens easily. But if I say you have to form iodobenzene from chloroalkene, if I say you have to form iodobenzene from your chlorobenzene, will this reaction happen with as ease as this reaction has happened? This reaction won't happen. It is difficult for your haloarenes to show nucleophilic substitution reaction. I minus cannot simply attack and break this bond and substitute Cl minus ion. The reason behind this is the strength of the bond that is between your chlorine and the carbon atom of the benzene, right? Since I minus cannot break this bond. You can understand the bond between chlorine and your benzene carbon is a strong bond. It is not easy to break this bond, and hence I minus is not being able to substitute your chlorine atom in the chlorobenzene. Why is it so? Why is chlorine and the benzene carbon bond is stronger than the usual normal carbon bond between carbon and halogen bond in the haloalkanes? This bond was easy to break. It breaks down and substitution reaction happens easily. But if I talk about this bond between chlorine and the benzene ring, this is strong bond. It cannot be easily broken, and hence substitution reaction is not easily observed in your haloarenes. Now let's understand why is this bond a stronger bond. The simple reason behind that is in haloarenes the halogen atom, as you know, halogen atoms have 3 lone pairs and they are in resonance with your benzene. The lone pair is in resonance. The lone pair on the halogen atom is in resonance with your benzene group. X has shared his one of the lone pair, a positive charge develops on it, and so on. The resonating structure goes on, and we have the hybrid structure which looks like this. In hybrid structure you show all the types of the bond, and we also have one partial positive bond. That's here. In haloarenes, due to resonance, partial double bond character exists between carbon of benzene and halogen atom due to resonance. It is stronger bond. It is stronger bond in comparison to the single bond that exists between carbon and the halogen atom in the haloalkane. One of the reason is the partial double bond. Another reason is that the carbon of the benzene atom, it has 3 sigma bonds, and we have already discussed whenever the carbon has 3 sigma bonds, it will show sp2 hybridization. sp2 hybrid carbon atom is more electronegative, than an carbon atom which is sp3, right? Than the carbon atom which is sp3. So what happens is, due to sp2 hybridization, the electron density between carbon and halogen atom is strongly held with carbon sp2 as well as halogen atom. Due to sp2 carbon of your benzene carbon, a stronger bond between carbon and halogen exists in your haloalkanes, whereas in haloalkanes your carbon atom was sp3 hybridized, it was singly bonded with the Cl atom. So these are the 2 reasons where we say haloarenes undergo very difficultly with nucleophilic substitution reaction, right? So these 2 are the reasons why haloarenes shows difficult nucleophilic substitution reaction. You can write carbon which is sp2 hybridized and the halogen atom bond is stronger than carbon sp3 and halogen bond. So it is difficult to break. Due to this reason, bonds are difficult or with difficulty. Bonds are broken with difficulty, and they show a very slow nucleophilic substitution reaction. They require high temperature conditions also, right? So the quiz is very easy. I've given very easy questions. The first question of the quiz is aryl halides are less reactive towards nucleophilic substitution reaction because. You have to tell me why aryl halides are less reactive towards nucleophilic substitution reaction. Chalo. Next question. This is the chemical reaction. What you have to do is you have to react this substrate with this. I'll give you a small hint. The nucleophile here is pH S minus. The nucleophile here is pH S minus, and you would be easily able to make it because it is phenyl S minus Na positive. You have to react the nucleophile. Just make sure where would you do the reaction with. Okay, so let's understand. When aryl halides are less reactive towards nucleophilic substitution reaction, aryl halides means aryl halides are your haloarenes. That is this. They are less reactive. We have already discussed this. This is because of resonance and sp2 hybridization of the carbon atom attached to the halide of the benzene ring. This is the reason. Correct option for this question is D. Okay, it is due to resonance as well as sp2 hybridized carbon atom. Okay, so next question is you have to show the reaction. Since you know that F minus is a halogen atom, it can show substitution reaction. You should also remember that SPH minus 2 acts as leaving group. It also can show nucleophilic substitution reaction. Now we have two leaving groups. One is fluoride, another one is SPH. SPH here is at the wedge position. Now what is the difference between A and B? It might look similar. A substrate has SPH on the wedge position, whereas SPH in B substrate has your on the wedge position. We'll on the dash in A it is on the dash position. It is dash, that is bottom of the plane is being represented. It is wedge position, that is the top of the plane is being represented. We'll do this dash and wedge dash projection in your stereochemistry. We'll do this in stereochemistry, but the question here was, will you substitute this or will you substitute this? We have two leaving groups. As you know, SPH S minus pH acts as a nucleophile. It is difficult to show nucleophilic substitution reaction in, with fluorine because fluorine is directly attached to the benzene carbon and it has a stronger bond. So fluorine won't be replaced. Fluorine here are not replaced. Fluorine here are replaced. Now B and C and D cannot be the option because they have replaced fluorine, which is not possible. Either the option is A or B. How do we decide it? We'll decide it according to SN1 and SN2 reaction. We'll discuss this later. In this reaction, SN2 mechanism is followed. In SN2 mechanism, we have inversion reaction that happens. Inversion means if in substrate your leaving group is at wedge position, the upcoming nucleophile will attach itself from the dash position. This is SN2 mechanism. We'll discuss this later, but keep in mind fluorine should not be replaced. It is SPH which will be replaced. This is SN2 mechanism. Inversion occurs since SPH in substrate was at wedge position. This will be at dash position. The upcoming nucleophile will be at dash position. The correct option for this question is option A, right? So this was it. We have completed. We'll also discuss ambident nucleophiles and we'll continue this chemical reactions of haloalkane part 3. Here we'll discuss what are ambident nucleophiles and do more nucleophilic substitution reactions with haloalkane. We'll also start with nucleophilic substitution reaction are further categorized as SN1 and SN2 reaction. We'll do this tomorrow. So we are meeting at 10:30 a.m. I hope you have liked the lecture. If there is any problem, anything that you want to discuss, or any priorities you have regarding the chapter, you can write that in the comment section. I'll check that out. Till then, we'll meet at 10:30 a.m. tomorrow with chemical reactions of haloalkane part 3. Thank you so much for watching.